Hi, I'm Gary, and I want to show you how I use Cloudy. In this video, we're going to talk about how the electron temperature is determined, the idea of thermal equilibrium. So, thermal equilibrium occurs when heating and cooling processes are in balance, so the thermal electrons have a well-defined temperature, a kinetic temperature. And so the way a large code would work is you would figure out what the heating rate was from various agents. In many instances, it's going to be photoionization. And then you would vary the thermal electron temperature until heating and cooling come into balance. And so equilibrium is when the system has been old enough and stable enough for this balance to have occurred. We have ways to check whether that's a good assumption. If you look back in the homework problem, the M16 model included the save ages command, and that includes some of the interesting timescales for processes in this model. And so what I plucked out is the cooling timescale. So this would be the timescale across so this is a function of depth across the model. This is the initial SIM16 model, so it does not go into the molecular cloud, stops at the ionization front. And we have a large H plus layer. So the ages command reports the cooling time in seconds, and this is a plot showing it across the nebula. So for most of the cloud, the cooling time scale is about 10 to the 9 seconds, a billion years. And for convenience, there's pi times 10 to the 7 seconds in a year. So it takes about 30 years for equilibrium to come into being in the H plus layer on NIM16. This cooling timescale depends on density. So for very dense regions, like a quasar cloud, it would be much, much faster than this. But for a very, very low density medium, like the intergalactic medium, it would be much, much longer. You have to compare these timescales with other timescales in the system for the things to change. And the biggest concern, which often you can't do much about, is going to be the star cluster that powers the whole thing. So stars are very short-lived, hundreds of thousands, fraction of a million years, and they have their own peculiar velocity compared with the molecular cloud. So there's a crossing time. And in the work I've done, it's been very challenging trying to find a crossing time because O stars have poorly determined velocities because of their line width. But generally, the crossing time in the cases I've worked on has been much longer than decades, usually longer than 100,000 years. If you want to do time-dependent MHD, Cloudy will do it. We do test this in our test suite nightly. There were two major studies done when this was newly introduced well, nearly 20 years ago now in these two papers. It's a lot of work. It takes a week or so to converge a model, and the model results don't change that much if you try to take into account the time-dependent non-equilibrium effects. And then at the end of the day, you don't really know what the history of the star cluster is. So you end up with a lot of more free parameters. So to a really, really good approximation, we're going to assume equilibrium. That's a good assumption. So what you do here is derive a heating rate. This is the cooling function we derived last time. You derive a heating rate, and this is going to be a magical heating rate. It doesn't depend on temperature. So it's just a horizontal line would be the heating rate. And then thermal equilibrium is where heating and cooling are equal. So there's usually uh, three regions where thermal equilibrium is possible. So in this instance, there's one at about 10,000 degrees, another bit of like a million degrees, and then another at 100 million degrees. If you had a different heating rate, so this is much smaller heating rate, there'd be still three possibilities, but only colder. So this would be over here at 1,000 Kelvin, at another one at about 3 or 4,000 Kelvin, and then another one at say 10 or 15,000 Kelvin. So three phases in equilibrium. Only two of these are stable. So the way you do the stability analysis is you set up a heating rate, then you ask yourselves the question, what happens if I change that heating just a little bit? So let's say we change it from the solid line up to the dashed line. How does the gas respond? This is a stable branch of the cooling function here. So if you were to take a stable equilibrium, and then if you were to increase the heating, so now before the gas responds, there's too much heating. So the gas is going to start heating up. So it's going to go right on this diagram. So if the gas starts heating up, the cooling goes up. And so it'll just go to a new stable temperature right there. So if you increase the heating, everything's fine. It moves over here. So this is stable. The same thing happens over here. If you increase the heating, the temperature goes up and the cooling increases. This is not stable. If you increase, if this is the equilibrium point and you start heating more, this will cause the gas to heat up and the cooling goes down. And so that's a mistake. So what happens here, I mean, you could have like a pin standing on its head, but if it's perturbed at all, it's going to fall over. And so what'll happen to gas here is it will either, if it's get disturbed down, if the cooling goes down, if the heating goes up, the cooling goes down, and then it'll get a lot hotter. It will jump over to this phase. And then the opposite, it will jump over to this phase. You may remember in some of the cloudy runs where you went deep, the comments after the last zone mentioned the cloudy encountered a thermal front. That's what we call when the gas changes phases. So what'll happen if you go into a cloud and if the heating rate is monotonically going down, if the heating rate goes down, it will follow this branch of the cooling function until it gets right here. And then if the heating goes down still more, the gas needs to find a place where the cooling is lower. The only place is way over here. So there's a discontinuous jump in the gas phase as it goes from here to here. So we call that a thermal front. And they do occur in nature because these double peak cooling functions are a feature. This really is how cloudy works. So in a cooling function, you have these areas shown in gray are thermally stable. And so any part where the cooling derivative is positive with respect to temperature, and I mean, if you want to do it exactly, you should include the heating dependence on temperature too. You want the net heating, cooling minus heating to be positive, to be stable. So there's four phases, three commonly observed. There's this phase, which is for human beings. If you walk out in your backyard and look at the Orion Nebula, you're looking gas on this phase at about 10,000 degrees. It jumps, the next phase down is a molecular cloud PDR phase. So this is gas at 1,000 degrees and below, a few thousand degrees and below, nice and stable. And then finally, there's a hot phase, which you see in astronomy in galaxy clusters, the intercluster medium. They're large regions. A lot of baryons are trapped up at these very high temperatures. Now, what's interesting is there is a stable phase at about 1 million degrees, which is not commonly seen. So we saw spectra last time. This phase is hard to detect because it emits mostly in the extreme ultraviolet, where it's hard to detect. You can't do spectroscopy. And so there should be a lot of gas up here. And although predominantly, when you looked at the spectrum, this gas in this phase emits strongly at regions we can't observe. It will emit a bit in the optical UV infrared. The signatures may be quite subtle. If you look out to nature, this is 30 Doradus, the brightest starburst in the local group. It's called the Tarantula Nebula. It looks like a train wreck. And if you look at it the right way, as Lisa Townsley did in this famous image where she's taken X-ray imaging and combined it with the infrared optical imaging, you see gas in three of the phases that are possible. And so you see the cool phase. I believe she used PAW emission as part of it. And there's the bright H plus layer, which is at 10,000 degrees. And then the blue gas is X-ray emitting. And so there's all three of these possible phases emitting all at the same time. What you made this image of a planetary nebula, much the same thing. The cooling functions aren't that different. And we see the bright optical emission star in the center. And then on the right, she's added in the X-ray imaging, and you see the hollows but appear to be hollows. They're actually filled with gases wrong phase to be detected in the optical they're X-ray emitting. So next time, we're going to talk about one more perturbation to this model. We're going to add dust to the model, and that's going to change things a lot. So see you next time.